So now we'll find the final expression for the Maxwell-Boltzmann law of distribution of molecular velocities. So we had this expression for DNC number of molecules, which is given by 4 pi Na cube c square e to the power minus b c square dc, where n was the total number of molecules in the gas molecules in the system, and A and B were two unknown constants whose value were not known, and we had to find their values. Now we have found their values, which is A is equals to m by root over m by 2 pi kt and B is m by 2 kt. Now if we put these values, then we have we will get the exact expression for DNC. Okay, so DNC is equals to 4 pi n, then A cube will be m by 2 pi kt whole to the power 3 by 2. Okay, so the power is half, and then we have to take its cube, that's why the power will become 3 by 2. Then c square, and then e to the power minus b is m by 2 kt, so m by 2 kt and this c square. Okay, so c square into dc. So this is the required expression for the Maxwell-Boltzmann velocity distribution law. So what does it mean? It means that suppose we have a gaseous system where there are total n number of molecules. You have a gaseous system, there are total n number of molecules. Okay, so out of them there will be DNC number of molecules which will be moving with velocity lying in the range c and c plus dc. Okay, so if we have a gaseous system containing n number of molecules and we want to find how many molecules are moving with a velocity lying in the range c and c plus dc, then we will find that the number is DNC. Okay, and DNC can be expressed by this term. Okay, and how DNC is related to C? By this equation. Okay, it depends on C by this expression. Okay, now in terms of number density, if you remember, the number density rho was given by n a cube e to the power minus b c square. Now in this equation also we can put the values of A and B. So A is m by 2 pi kt. Now there is cube, so it will become, the power will be 3 by 2, and then if we put the value of B, it will be m square by 2 kt. Okay. Now if we take DNC by n, then it will be 4 pi. See over here, DNC was 4 pi n and rest of the term. So if we take DNC by n, okay, so if we take DNC by n, then it will be, the term will be rest of the term without n. Okay, so it is 4 pi m by 2 pi kt whole to the power 3 by 2 c square e to the power minus m square by 2 kt into dc. Okay, now we'll replace this term, okay, by f. Okay, so f is given by 4 pi m by 2 pi kt whole to the power 3 by 2, then c square e to the power minus m square by 2 kt. This f is called Maxwell-Boltzmann velocity distribution function. Okay, now next what we will do, we will plot the graph for f versus c. Okay, so it will look like this. So along x-axis we are plotting c, and along y-axis we are plotting the distribution function f, and it will look like c, where f is given by, of course, this expression. Okay, so you see, okay, so when c tends to 0, okay, and c tends to infinity, you see the f, which is equals to DNC by n, equals to 0. Okay, so at c tends to 0, the f become, the distribution function becomes 0. Also as c approaches infinity, that is very high value, then also the distribution function, as you see, this line is going parallel to the x-axis, means at c tends to infinity, it will also become 0. If you put c infinity over here, then it will be 0, right? So if the distribution function will be 0, it means that DNC will be 0 for the velocity approaching 0 and infinity. It means that those molecules which have velocity tending to 0, means which have very smaller values and the molecules which have their velocity tending to infinity, means very high value, their number is quite small. That is, in a gaseous system you will find very few molecules will have very low velocity or very high velocity. Okay. Now you see, if you look at this expression, the distribution function depends on two terms involving c. One is c square, another is e to the power minus m c square by 2 kt. Okay, so as the velocity c increases, c square increases, but this exponential term decreases. Okay, so what will be the so with the increasing of or decreasing of c, how f will change? It will depend on the combined effect of these two terms, because one term is increasing with increasing c, another term is decreasing with increasing c. So what will be the how f will change with increasing c? It will depend on the combined effect of these two terms. Okay, so first we'll consider that this condition when f is when c is increases. Okay, so we know when c increases, the c square increases and the exponential term decreases. Okay, so and what will be the combined effect as c goes from the smaller value to the higher value? Okay, so for smaller values of c, out of these two terms, c square is more dominant, okay, than the exponential term. So as a result, the distribution function also increase, and it increases quadratically, means as a square of c square. Okay, so for smaller value of c square is more dominant than the exponential term. As a result, for smaller values of c, as the velocity c increases, the distribution function fc also increases, because it depends more on the c square term, and it increases quadratically. That's why for these smaller values of c, as you see, as c is increasing, the value of f is also increasing, and it is following the quadratic nature, which is c square. Okay, now if c increases further, then the exponential term becomes more important. That is, now it will dominate over the c square term. Okay, so as a result, what will happen? Initially the curve was increasing, but as c all increases, the exponential terms becomes more important, so it reaches a maximum. Then the exponential terms will dominate over the c square term. Then the curve fc will decay exponentially. So we can say that as c increases, as the exponential terms becomes more dominant, the curve increases quadratically. Initially for smaller values of c, due to c square, it attains a maximum. Okay, then it decays exponentially, because for this region the exponential term dominates over the c square term, whereas in this region the c square term dominate over the exponential term. Okay.